Okay. Welcome to lecture 4 of the Toolkit series in the spectral method section. So today we'll continue our discussion on the random walk matrix. We will try to understand when does a random walk matrix have an eigenspectrum. And this will lead us to the important notion of reversibility of random walks. And we'll then focus our attention only on reversible random walks, try to understand when do these random walks converge, what's the rate of convergence. We'll define the stationary distribution, talk about the convergence of stationary distribution, and try to understand that. And then we'll try to look at something which is commonly called as the expander mixing lemma. This is a very powerful tool which will be repeatedly used in several applications, at least in theoretical computer science. So let's do a quick recall from last time. So we have defined the random walk matrix. This was any matrix. So there's a state space V, which is a state space. And for the purposes of this, we'll just assume this is a finite state space. Everything that we do be a finite state space. And there's a matrix W on RV cross V, where WU comma V principle denotes the probability of going from vertex U to vertex V. So in general, this is a row stochastic matrix. We have for all U, we have summation WUV equals 1. And these are all non-negative matrices. The random walk matrix. A special type of random walk matrices are those that come from weighted undirected matrix, undirected graphs. General is weighted directed graphs. In this case, the weighted directed graph, the W, so given weighted adjacency matrix AG, the walk matrix WJ is defined as WG of UV is just AG of UV divided by degree of U. And degree of U itself is the sum of the weights incident on U. Yeah. So this one. So that's the special case of weighted undirected graphs. That's one kind of random walk matrices, but more generally, it's weighted directed graphs. And we had seen two types of operations. We had seen left and right multiplication. So when you're multiplying the matrix on the left, that is, you have a function f on RB going from R to, look at it as V to R. Then mapping F being mapped to MF is sort of, this tells you how the function changes as you take a step in the random walk. The expected value of function. Then, and we had some of what observations we saw was this: the all ones is an eigenvector with eigenvalue 1. Okay, this is something we had observed. I want to ask another question. Can there, suppose there was another eigenvector with some other eigenvalue, can that eigenvalue be larger than 1, smaller than 1? Why? So this is what MFU we had, sorry, this is WFU, sorry. We have defined it. This is how matrix multiplication works. So the youth entry of WF is exactly summation UV. Notice that this sums to 1. So this is an averaging. So FU is only going to get averaged out. It can never, the eigenvalue vector values can never be larger than 1. So this can never return values which are, consider the maximum value, it can never, this is just averaging whenever you're left multiplying by the matrix, you're only averaging entries. Therefore, you can never get eigenvalues more than 1. So in particular, among the observations I want to say is actually all eigenvalues have absolute value at most 1.
I have to take the U where F is max.
Yeah, take that and use max, and it will never. So take the absolute value and then you'll get the absolute value statement. This can never. So eigenvalues, and you know that there is one with eigenvalue 1. There could be several of them. Let's now ask: are there? So let's ask how large is the eigen. So far I haven't yet told you there's a full eigen spectrum. We haven't yet gone to the theorem, but all of these can be made with just this observation. Just the fact that we have this, if an eigenvalue exists, it has to be an absolute value at most 1. The next question I want to ask is, how large can the eigenspace corresponding to the eigenvalue 1 be? We know it has at least dimension 1 because of the all ones vector. Can there be more to it? We already have some idea of it. When does the largest eigenvalue? Think of it as being an undirected regular graph. When do you have more than one eigenvalue of the largest type? When it is disconnected. So, and that's true. Disconnected, you can just have all ones here, 0 here, or all ones there, 0 here. Those are this ones. So let's try to get rid of the disconnected case. In the random walk, so in the case of graphs, it's easy to say disconnected just means that there is a path from every vertex to every other vertex. In the case of random walks, so we're going to introduce this important notion of irreducible random walks. Which exactly amounts to the same thing. It says between any two vertices, it's basically going to say, so for all, let's say W is irreducible if for all pairs of vertices UV in the state space, what should we have? I can't say WUV is greater than 0 because that says I had to have in a single step I should be able to reach. What we can say is there exists some time t such that WTUV is greater than 0. That is W, we saw that this is W is corresponds to a random walk of 1 step. W square is random walk of 2 steps. And in general, WT will correspond to a random walk of T steps. All I'm claiming is from every vertex to every other vertex, there must be some time T. This T could depend on the U and V, such that there's a non-negative probability of going from non-zero positive probability of going from U to V. So we'll define this notion of irreducibility, and we'll work only with irreducible random walks. Because otherwise you can just decompose it into each part separately and just work with them. This one. So we'll work. This is the corresponding notion of connectedness for random walks. Want to say if W is irreducible, then the eigenspace corresponding to eigenvalue 1 has dimension 1. In other words, the all ones vector and scalings of the all ones vector are the only guys that live in the let's see a quick proof of this. So let F be, we have already seen the proof of it a few minutes ago, any eigenvector corresponding to eigenvalue 1, that is WF equals F, that is for all U in V. Better I write W F of U, sorry, we have F of U equals WF of U, which we know from above. WF of U is this quantity, V in V. So we have this. I want to say if you have irreducibility and this, you're already done. Why? You see a proof of this. If F is an eigenvector for W, so F will also be. So let's make one more observation. So notice that it observe F is also eigenvector for WT for all T, and the with eigenvalue 1. Now I want to claim, suppose F is not a constant vector. Suppose S is not the constant vector. I want to tell you that inequality is going to give you a contradiction. Let's do the same argument which Varun had said before. Let's pick U to be argmax of V of F, FV, the largest F. Let's call it U max. And furthermore, let's and let FU max equals say M. Suppose FV was less than, I'm taking FV, taking the FV which is the maximum.
It should be U plus the real number.
No, it's not the maximum quantity, it's the argmax of it. It is the V that attains, it's the argmax of it. That's right. It's not maximum, it's the argmax of it. And so the maximum is M, and the maximum is M, and the value at and the point at which it attained is this one. So suppose FP is less than M. WTUV FP. Do you see a contradiction somewhere going on here? So V prime appears with a non-negative value here. This is an averaging of these quantities.
That's where most are.
See, even if one quantity is less than M, that quantity has to be smaller than M. So in particular, it tells you that everything has to be equal to M. This is the same argument we have seen before. This will tell you.
So Prahlad, is it WTU max comma V or
Yeah, sorry, you're right. Contradiction. Hence.
It's lesser than M.
Huh? Sorry, what did I say? F max is less than M. Hence, FU equals M for all U. Therefore, once you have irreducibility, this is the same proof as over, it will just percolate. There can be the eigenvalue vector corresponding to the largest eigenvalue is unique. It's single dimensional. It's the constant vector. There's no other vector. Let's not discuss this.
So there is one T, I mean for all V, there is one T such that
There's no. For all V, for every pair UV, there is one T such that W2 T UV is greater than 0.
right, but here, so these are all different types.
These are different. I don't care. That is, suppose there is some FB prime less than M. Then WT UV prime is greater than 0 for some T.
It's
For some T, which is actually a function of this V prime. Let's look at this equation for that T. Even in that T, one quantity here is less than M. This is an averaging of several quantities. Even if it's if one quantity less than M, that quantity will have to be less than M. Because this is an averaging going at that step.
You could also take an T to be T mass across pairs. Instead of
I don't know if I can reach in the T step, I can reach in the T plus first step. No,
not.
it's not monotone. I'm not accumulating probabilities. It could be, for example, a bipartite graph at this point of time.
And then the helpful necessarily.
But that should be the W, the entries are all non-negative.
Yeah, but the graph could be bipartite. I haven't ruled that out yet. We will rule that out shortly. The graph could be bipartite.
But here, all you need is you take the eigenvector corresponding to the maximum eigenvalue. We take the coordinate that's maximum and we take some coordinate which is not maximum.
Not maximum.
Take that pair.
Take that pair.
Choose the T on the basis of that pair.
Okay. Yeah. So in principle, what you said is I want to because I want to talk about the stationary distribution, assuming the least amount of piece of information. I don't want to talk about the least eigenvalue and all of that. That's when the bipartite graph will come. So right now I'm using as little as possible, just the basic definition of the random walk and irreducibility of the random walk, which is needed for this point. Only irreducibility is needed, and irreducibility tells you that the eigenspace corresponding to eigenvalue 1 is dimension 1.
What if the value where f is maximum supported on multiple places?
Just pick one of them and do it. All I'm claiming is they can't be one at the max and another one is less than max.
That should be a constant vector.
It should be a constant vector. That's all I'm thinking. It should be a constant vector. By the way, all of this discussion was done with when you're multiplying the random walk matrix on the left of the vector. We also saw what happens right multiplication. And we saw that this corresponds to sort of one way of viewing it is view the input. Technically, right multiplication is you can take any, in particular, you can take any G going from R to V to R and look at the map going G transpose being taken to G transpose W. We could have done this or equivalently G being taken to W transpose G. If you look at it, I'm viewing all functions as column vectors for me. And this is true for any vector, any real valued vector. But we saw that it has a special meaning when this vector actually looks like a probability distribution. The step if this G was actually a probability distribution over the vertices, over the vertices, then this step going from P to W transpose P is one step of the random walk. How the probability, we saw this last time. I'm just recalling things we did in last time. Now notice that left eigenvectors are solutions to WF being 0. Right eigenvectors are solutions to W transpose F being 0. They are solutions to this. This is exactly the column space or the rank space. These two we know column rank is equal to row rank. Therefore, the right eigenspace is also of dimension 1. Just from, we get it for the right eigenspace is also of dimension 1. Questions I want to say? The space WF is 0 has dimension 1 if W is irreducible. This we already observed. Hence, the space of G such that W transpose G is sorry. What did I write? So the way to write this, strictly speaking, to write this should have been W minus I times F is 0. So that one has one. So similarly, the solutions for this are also has dimension 1, since row rank of W minus I is the same as the column rank of W transpose minus I transpose, which is I itself. And so there is an eigenvector. We are going to normalize this eigenvector so that its value is sum to 1, and this will be what's called the stationary distribution. There's one catch to it. Why should its values be all positive, all of the same sign? That you could have positive and negative entries. You know it's of dimension 1. So let pi be a solution to G to W transpose G equals G such that summation pi V equals 1. So I'm trying to make it a probability distribution that will ensure it sums to 1. It doesn't still ensure that it is non-negative. All of them are non-negative. Okay. So we will see a full proof of this for the case when it's an undirected graph. It's a directed graph. We will come to that also. Let's look at the special case when W arises from a directed graph. Sorry, undirected graph. Then I actually want to say you can explicitly tell me what is a pi that satisfies this property. When you tell me what's a pi that satisfies, you have a graph which is even think of it as unweighted. You have a graph which is just an undirected graph. What is a probability distribution that remains unchanged
by D.
If you take it proportional, not 1 by 2, if you take it proportional to the degree distribution. So that you take the degrees of the vertices. So let's consider G to be equal to degree of G of V to be degree of V divided by delta, where delta is the sum of the degrees. It's not hard to see what's WG of, what is W transpose G of U. This is summation W transpose UV GV. Summation over all V. This is therefore the same as WVU GV. What is that? That's WVU itself was what? It was the adjacency matrix VU divided by the degree of V. That was what WVU was. What is GV? GV is degree of V divided by delta. So you get 1 by delta summation AGVU. The summation over what? What is that? That's the degree of U. Which is G. That is, this G is actually a eigenvector for, is a right eigenvector for W. And it's a probability distribution. So at least in the case of the undirected graphs, so G, so pi given, we define pi to be this, pi defined as pi U equals degree U by delta is a stationary distribution. In fact, by what we have said, it is the stationary distribution. It's the only vector that can satisfy this. It's a right eigenvector, it's of dimension 1. Therefore, there's only one of, anything else should be a scaling of this. Therefore, this is the only guy which is the stationary distribution for irreducible matrices. And this the here comes because of irreducibility. Yeah.
So for irreducible random box, we've seen that there is only one stationary distribution. And so irreducible, I should just think of it as
no, we have actually for all this one we have irreducible and actually undirected only we have seen one stationary distribution. We haven't even seen that there is a stationary distribution for directed.
and let's say we are in the direct world, then irreducible means there is this stationary distribution. But now if you take an arbitrary, like, let's say the random walk has, let's say 2 components.
Yeah.
The left component by itself has a stationary distribution. The right component itself has a stationary distribution. So if you just take the concatenation of these distributions.
But you can do anything. No, you can scale them, and whichever you have, any convex combination of them is also a probability. Any convex combination of them is a probability distribution.
But okay, but then we can say that it's like if you take all of the, I mean,
yeah, that's all, because it's of dimension. It's the dimension of the space is exactly the number of components. Therefore, it will exactly be all possible convex combinations. That's true.
Okay,
that is true. Yeah, but it doesn't add anything to it. So we'll work only on each connected part. Now, so this proof only worked for. This proof only worked for. So suppose W is a directed weighted graph. Even then, you can show that there exists stationary distribution. So I don't know of an elementary proof of this. That is, there is elementary proof, but it will take long. But I'll just prove there's a one-line proof of it. Which look at delta n, which is the simplex. What do I mean by this? It's a set of all functions g from v to r greater than or equal to 0, such that summation of gv is 1. It's all probability distributions on them. And we have a map. We do have a map now going from delta n to delta n, no, which is just g being mapped to w transpose g. This is a map on a closed compact. It's a continuous map on a closed compact. By fixed point theorem, it has a fixed point, and that is the stationary distribution. It has to have dimension 1 by what we said before. So delta n is closed and bounded. And above, hence, by fixed point.
Why is delta n close to 1?
That's delta n. It's a delta n is just set of probability distributions. There's things with sum to 1. So it's a closed and bounded set. You have a continuous map from a closed and bounded set to itself. There has to be a fixed point. I'm using Brouwer's fixed point theorem. It's pulling something out of the heart. It's not elementary, but it's a quicker, fast way to see why any random. This tells you any random walk has a stationary distribution. It doesn't have to be irreducible. Any random walk has a stationary distribution. If it's irreducible, furthermore, the stationary distribution there is the unique stationary distribution. Okay.
So why does the above proof not go through? Is it because the degree can be 0 in there?
The above. Oh no. So we used in degree equal to out degree. Here AGBU. That's the out degree of the vertex U. That's not the in degree. This step, I've used that as the out degree. The out degree and the in degree are, that step I'm using, that's this equality. What you said is true. This equality over here, from here to here. In fact, let's point that, make that one. From this transition, this is where you're using undirectedness. Important. And that proof breaks down otherwise. Of course, there's a super clean proof of it, but I'm using the fixed point theorem for this. There are other ways to prove this. So if you look at any random walk, textbook on random walk, because they would like to talk about the stationary distribution without introducing more notation. There's another way of introducing this without bypassing the fixed point theorem. But this is the time-wise, it's the most efficient way of showing there is a stationary distribution, and by what we said due to irreducibility, this is the stationary distribution. Okay. Well, that is fine, but we would like to understand the eigenspectrum of it. So for that, we would like to understand, we would like to look at if it has a full eigenspectrum, we want to reduce things. For that, we need this random walk matrix to be self-adjoint under some inner product. The question is, so we want to understand, the next goal is going to be trying to understand the eigenspectrum of a random walk matrix. And you should already know by now that we can't work with the classical dot product being the inner product, because for something to be adjoint under that, W has to be W and W transpose have to be the same. This one, and it is not. This degree by this one. For example, this, where did I put this? This very beginning. So here, that is W is D inverse AG. So even though AG is symmetric, D inverse, this happens on this side. So the product of two symmetric matrices need not be symmetric. Okay. So what we'll try to ask is, there another inner product? The thing was, actually, the usual inner product, the dot product, treats all the vertices equally. Now, you should not be treating the vertices. There's just something we already understood when you have a random walk here. For now onwards, I'll only be talking about irreducible random walks. There is already the stationary distribution sitting. Once we are talking about irreducible random walks, there is the stationary distribution sitting on the vertices. So certainly vertices should be weighed by the stationary distribution. You should not be looking at things, all vertices equally. If a graph was regular, the stationary distribution will be the uniform distribution. But if the graph was not regular, the stationary distribution could be something else. So what we'll define what is called the pi inner product. The inner product influenced by the stationary distribution. Pi is the stationary distribution of W. So inner product of.
So here we are looking at right. The matrix is on the right.
Which matrix?
When we talk about eigenspectrum.
So eigenspectrum just is going to talk. We're going to talk about right eigenvectors, left eigenvectors. Eigenvalues will be the same. Eigenvalues will be the same, and we will talk about right eigenvectors and left eigenvectors. Eigenvalues, of course, will be the same set of eigenvalues. So two functions GH. We will now define it as expected value over pi GV HV, or equivalently summation pi V GV HV. Is that clear? So it's the usual dot product except for this pi V term over here. And it should be clear why we should have the pi V. We have the stationary distribution. Stationary distribution tells why some vertices are heavy, why some vertices this one. We will weigh the vertices accordingly. And so this is the inner product. This is the most natural inner product to use on the functions. So whenever I'm talking about this inner product, I will subscript it with pi. Is the inner product clear? The definition of the inner product. It's a very natural definition. Let's ask, what's the adjoint of W under this inner product? What's the adjoint of W? It is that. So the adjoint of W star, is the unique matrix that satisfies GWH pi should be the same as W star G H pi for all G and H functions on the. Let's quickly see what this W star has to be. And then furthermore, in order to be self-adjoint, we will now put conditions what W star should be. The W star should be W if eventually we want to understand one. So let's look at the inner product again. Let's look at GH. Sorry, what did I put? Yeah, GH pi. Once again, what did we see? This is just pi V, GV, HV. So this can be written as G transpose pi H, where pi is the diagonal matrix with the stationary distribution on the diagonal. This is just shorthand for this quantity. Is that right? Multiply H by pi H and then G transpose. This is just this quantity. So with this notation, let's look at what GWH pi is. This is just G transpose pi WH. Whereas what is W star G H pi? This is W star G transpose pi H, which is G transpose W star transpose pi H. Right? So in other words,
All GH, right?
so this is for
These are
all
equal.
for all GH, we must have these two should be equal, which means as two matrices, those two should be equal. This is equal for all GH. Hence, pi W should be equal to W star T. So let's actually look a bit ugly this way. That looks a bit ugly this way. Let's just apply transpose everywhere. So I want to define what W star is. Let's just apply transpose everywhere. So you get W transpose. So the transpose of a matrix is the transport of a product is a product of its transposes, but written the other way. So W transpose, pi transpose, but pi transpose is pi itself. Pi W star. That is W star is equal to pi inverse W transpose pi. That's what W star should be. This is the matrix that does it. Now, furthermore, if we want self-adjoint, if W is self-adjoint, under this one, then we must have the condition is basically pi inverse W transpose pi, or equivalently pi W should be equal to W transpose pi.
Self-adjointness was needed for the spectrum.
Self-adjoint was a sufficiency condition for you to have a full eigenspectrum.
And that argument, the proof that self-adjointness suffices. For
Yeah.
This, that proof is robust to what bilinear form we are using for.
It didn't matter which. But then you will get an orthonormal system under that bilinear. You will get a full this one.
The product will be
under that bilinear. So you will get the eigenvectors. Eigenvectors doesn't care which inner product or orthonormal. Do not care. But you will furthermore get that these eigenvectors will be orthogonal under this particular inner product. Okay. This condition is called this condition is called reversibility, and we'll just quickly see why this is called reversibility. So reversible. So if this is W is reversible if this condition is satisfied. Phi W is W transpose pi. And I'll just justify the name reversible. If you look at that, what is that? Those two are two matrices which are equal. That condition, this star is equivalent to pi u WUV equals pi v WVU. This is, you start from the stationary distribution and you take an edge out of it. So you pick a vertex according to the stationary distribution and then you pick the edge out of it. But this is, you start with V and you take an edge out of it. This says it doesn't matter how you pick it. It's sort of like the undirectedness of the graph. That is, this is the probability of picking this edge. You pick a vertex at random and pick an edge going out of it. It didn't matter whether you pick which one has a start vertex. Whether you picked U and then took the edge out of it, or you picked V and the edge out of it, the edge UV. Once you do this probability of picking it up, you don't know whether you came from U or V. You just know the probability. So in other words, if you are on the stationary distribution, if you take 10 steps in the stationary distribution, if I tell you the 10 steps in the forward direction or in the backward directions, you cannot tell which is which. The distribution looks identical. So here, basically here, if I give you the pair UV, you cannot tell me, and I tell you the way I picked UV is I first picked according to the stationary distribution and then took an edge out of it. Then you can't tell if UV is different from VU. That's what this is stating. In other words, this walk on according to the stationary distribution, if you see the sequence sampled according to the stationary distribution on the random walk, if you see this movie in forward direction or reverse direction, they look identical. As a distribution, step by step, they look identical, and that's why it's called reversible. Okay. Yeah. This is equivalent to this. And there are multiple names for it. It's called time reversibility. Detailed balanced condition. And once you have this condition, we have the eigenspectrum. So let's just write down. So the spectral theorem guarantees. Spectral theorem guarantees that every irreducible reversible random walk W has n eigenvalues, lambda 1 greater than or equal to lambda 2 greater than or equal to lambda n. These all belong to the reals. And we already saw the largest has to be 1. The others can only be smaller. And in fact, the others smaller also, this has to be greater than or equal to -1. N left eigenvectors F1, which is the all ones vector, F2, Fn belonging to it, such that Fi, Fj, according to the pi inner product, is exactly delta ij. and WFI is lambda I. The spectral theorem guarantees this. Okay. We'll also ask what are the right eigenvectors. The left eigenvectors are this. Right eigenvectors also. I want to actually. Right. We also have right eigenvectors. Spectral theorem will also guarantee right eigenvectors. The way we stated spectral theorem, it only guarantees left eigenvectors. We only talked about things on the left. But we will quickly see in a minute or so, we will see what are the right eigenvectors. We'll infer it from these objects. Is this clear so far? What about? So these are the right eigenvectors. So given a random walk, which is irreducible and reversible, we know its eigenvalues are between 1 and -1. 1 is certainly attained, and it is a single eigenvector, and corresponding to single eigenvalue corresponding to the eigenvector all ones. And then you have eigenvectors for all the rest, and it forms a nice orthonormal system under the pi inner product. Now, what about right eigenvectors? So we know one of them already. The stationary distribution is, so we are asking for whatever vectors, that is, we are asking for vectors of the form W transpose P equal to some lambda P. These are the vectors we are asking for. We know one of them already. We know, for example, we already know W transpose pi equals pi. So that's an eigenvector with eigenvalue 1. It's a right eigenvector with eigenvalue 1. But notice we know something about W transpose. Reversibility guaranteed to us. W transpose is exactly that quantity. So what was W transpose? Let's recall that. We are working with reversible matrices now. So phi W is W transpose pi. Reversibility guarantees to us that it implies W transpose is phi W pi inverse. That's what we had. I think I got the thing on the right. Yeah, it's phi W pi inverse. This should tell you if F is an eigenvector with, immediately tell you if WF is lambda F, then I want to claim pi W pi inverse pi F. What is it? So pi inverse of pi F is F, WF is lambda F. You get this one, so you get lambda pi F. Therefore, if F1, F2, Fn were the left eigenvectors, pi of F1, pi of F2, pi of Fn have to be the right eigenvectors. And that's clear. Pi of 1 is pi, is the stationary distribution pi. The right eigenvectors, right, hence corresponding to lambda I is pi F. And of course, pi of F1, which is pi of the all ones, is the vector pi, which we. So it's all the left eigenvectors and right eigenvectors for this just differ by multiplication by pi. Questions? I'm going very slow. I want to say, so far we talked about reversible. And once again, let's look at the reversible condition again. Reversible condition was what? It was pi W was W transpose pi. Let's look at the matrix pi W. What's the transpose of the matrix of this matrix? This is W transpose pi, which is pi W. So even though pi W is not a symmetric matrix, pi W is a symmetric matrix. That is, hence pi W is symmetric. Notice W is just pi inverse of pi W. Why am I doing all this nonsense? Recall when we had an undirected graph, W was the degree inverse times the adjacency matrix. The adjacency matrix was some symmetric matrix multiplied by D inverse. This is also some symmetric matrix multiplied by pi inverse, which is actually proportional to the degree. This one. This says that if a walk is reversible, there is an underlying undirected graph corresponding to it, which basically, the walk is reversible basically tells you going from U to V or V to U is the same thing. Therefore, there's an undirected graph. So reversible random walks are exactly random walks on undirected weighted graphs. Reversible random walks is the same as random walks on undirected weighted graphs. These are the exact same thing. And only for those we have the eigenspectrum, full eigenspectrum. The others we don't have, and our focus will only be on these objects. Okay. Okay. We have about half an hour left. We will take the eigenspectrum and prove some properties of the underlying random walk. Now, you take the random walk on, you're given a reversible, irreducible random walk. You have the stationary distribution pi with the unique stationary distribution. You also have the full eigenspectrum. You can ask, if I keep walking, start from some arbitrary probability distribution, if I keep walking on this, will I converge eventually to the stationary distribution? So let's ask. I'm going to ask a question. The next topic is going to be convergence. Of random walk. So P, an arbitrary random walk, arbitrary starting distribution, P naught, call it starting distribution. Say possibly entered on a single vertex. Its some are this one. And let's look at the random walk, which is P naught going to W transpose P naught, going to W transpose square P naught. So we will call these guys naturally. This will be P naught, P1, P square, PT. Question we want to ask is, does PT converge to the stationary distribution? Notice if P0 had been pi, this would have been the stationary distribution every single time. You didn't have altered at all. But otherwise, do you go close to the stationary distribution? That's what I want to ask. For that, let's ask, what are the things that prevent you from going to the stationary distribution? One was certainly, if it was not irreducible, it was disconnected. So in particular, what does disconnected mean? Disconnected says that W, the second eigenvalue, was also 1. So the gap between lambda 1 and lambda 2, the fact that lambda 2 is less than 1 is telling if lambda 2 had been 1, that would have been a bottleneck to this one. You need it to be converged. So I want to ask, what are bottlenecks to convergence? One is, of course, lambda 2 being equal to 1. That is, if lambda 2 is not separated from, this is a bottleneck. But we already assumed irreducibility, so this is not the case. If W is irreducible. But what about, we had discussed one other example of a case in which the graph will not, we had talked about it early on. So graph is bipartite, yeah. So then the random walk is just going to keep moving back and it will never converge. Every even step it will be on one. Suppose it started off with the vertex on one side. Then at every odd step it will go to the other side. Every even step it will be this side. It will never converge to any fixed distribution. It's going to keep going back and forth. You want to prevent this also. Other thing is the bipartiteness is another. And you will prove in your homework that bipartiteness is equivalent to lambda n being minus 1. So if either lambda 2 was 1 or lambda n was minus 1, these two will prevent you from this one. So you will ask how far. So we'll come up with this notion called lambda, which is max of lambda 2 and minus lambda n. Or let's just put it as mod of lambda n. If this quantity is separated from 1, I want to say, then those two things, then those two obstacles disappear. What we'll now show is if this quantity is separated from 1, is away from 1, then actually the random walk will converge to the stationary distribution. Those are, in other words, those are the only two obstacles. If you don't have those two obstacles, which is if lambda n is not minus 1 and lambda 2 is not 1, then the graph will converge to the stationary distribution.
In the second one, you don't have, not only bipartiteness, any k-partiteness will give you problems.
What do you mean by k? Let's look at a three-partite. What's a three-partite graph?
3 sets and edges between the 3 parts.
So that will mix, no? Because each time you have a chance of going to the one of the other two, and then it has possibility of mixing off. It's not stating that at every step, it's not because of the undirected nature of the graph. Once you have a three-partite graph, right? Suppose you start in only one part. There's a probability that you might go to this either the part on the right or the part on the left, and then you have chances of it getting mixed up. If it will mix slowly, but yet it will mix. So we will show that the graph is k-partite.
I think what you mean is the picture could be that you have 3 partitions and there are edges going like this.
But
then you can make it bipartite. Bring that in.
So if it's three-partite and edges going only from 1 to 2, 2 to 3, 3 to 1, then you are doomed.
Yeah.
But this is the undirected, we are working with undirected graphs. If you go from 1 to 2, you can also go from 2 to 1. So three-partite is not a problem for us.
No, second it go from 1 to 2 to 3 and then 2 to 1 and 3 to 1.
Yeah.
Is that
That's a problem, no? Suppose you had a directed graph in which all edges either went only from 1 to 2, 2 to 3, and 3 to 1.
that's one complete cycle?
One complete cycle. Then you have a problem, no? Because every third step will be in a different part. It can never this one. But we are not working with directed graphs at all now. To have this example, you have to have a directed graph. To have a three-partite structure which you talked about. The undirected three-partite is not a counterexample. Suppose you have an undirected graph. So for example, a triangle. I want to claim on a triangle, you start a random walk. It will converge to the stationary distribution. In fact, we will prove it. So you can't have any objection to. In fact, on a triangle, it will converge. On a directed triangle, yes. But we are not going to be talking about directed triangles. All walks we are considering is basically walks arising from undirected weighted graphs. Okay. So what we'll try to understand the total variation distance of between PT and PT, which is the probability distribution of the Tth step, and the stationary distribution pi. What do I mean by total? This one. So pi t is one stationary distribution, pi t is a probability distribution. I'm talking about the total variation distance. This is just summation 1 PTV minus pi v. And there's a half. That's the total variation distance. So we will now try to relate it to, we'll use the eigenspectrum to analyze this. Things are going to, how am I going to prove this? So ideally, we can try to handle this. So the way we're going to handle this is ideally now, because we are working in the pi inner product, all summations with v, it's best if there is a pi v sitting in front of it. It should always be weighted summation. So let's make this also that way. This is half of summation v pi v PTV pi v minus 1. Okay. I can write this as v pi v. This is the matrix pi inverse. I want to write this in vector notation. I want to write this as half of, let me write down and then you will be convinced of what it is. Pi inverse of PT minus the all ones vector. It's one norm, but in this pi world. Where what do I mean by one norm of a vector? Where x k pi norm is the kth root of summation v pi v x power k. It's the usual kth norm definition, except that I'm averaging with respect to pi. Is that okay? Whatever I've written here, this is just not done nothing. It's just given a name for the notation that we had before. The reason I want to write everything in the pi version is because I have pi inner products. Everything happens in this one. Now Cauchy-Schwarz will tell you that this is less than or equal to half pi inverse PT minus the all ones vector, but in the 2 norm. This is just Cauchy-Schwarz.
Is there a absolute value for x of v or no?
This one? Yeah, here, yes.
Okay.
Sorry, yeah, there is an absolute value. So we have this inequality, that is the total variation distance between PT and pi is at most the 2 norm between pi inverse PT and the all ones vector, but under the 2 norm being taken in this pi inner product space. So let's understand how does this quantity change as p varies. So let's look at this quantity. Let's look at this quantity pi inverse PT minus 1 to pi. How does it change when t goes from t to t plus 1? The way we'll do it is we'll just write PT in its eigenbasis and find out how to change it. Okay. So we'll write PT is a probability. It's a right eigenvector. So we'll write it in terms of the right eigenbasis. And notice it works very nicely. Right eigenbases are all things multiplied by pi. The pi will very nicely cancel out with this. So it will work. And so all we're going to do, the rest of it is going to be just we're going to write everything write the whole thing in the eigenbasis, which we already have, and find out how things are going to work.
Sorry, so this pi inner product, etc. Cauchy-Schwarz works as it is.
Cauchy-Schwarz is just expected value of f square is less than or equal to expected f, or the other way, or the other way around, is greater than or equal to. That didn't care what the pi's were, no? That's Cauchy-Schwarz. That's all I'm being used.
So here, I think we're subtracting a matrix from vector.
Yes, not a matrix from a vector. This is a matrix. Pi is a matrix. This is a vector. Therefore, that's a vector. It's a vector minus a vector.
Oh, one is
The all ones vector. So I'm looking at even that happened even at the step above. That was just short notation. I removed that summation v, and so that got into that. It was just. Okay. So let's write PT in the eigenbasis. So PT itself is some summation alpha I pi fi, where fi's are the left eigenvectors, and hence pi fi's are the right eigenvectors. I'm just writing it down.
But there are changes.
That case of Jensen is called Cauchy-Schwarz.
Birds.
Huh?
Okay.
Convexity.
It's convexity, that's all. So you can write pi t in this one. So in particular, let's look at them. It's alpha. Let's write it. This alpha 1 pi 1 plus I greater than or equal to 2 alpha 2 pi f2. I'm writing the first one separately, which is just alpha 1 times pi. Is that all okay? Nothing so far.
Alpha I.
Yeah. Let's find out what is alpha 1. The orthonormal system, what is alpha 1? For 1, notice alpha 1 is exactly PT inner product with pi. That way. Easier for me to have. Again, better for me to write it. So if once we have this, I can also write pi inverse PT is equal to alpha 1 1 plus summation alpha I fi I greater than or equal to 2. What is alpha 1? Alpha 1, this is exactly equal to pi inverse PT inner product with the all ones, but in the pi norm. That's how you get this. But what is this? This is summation B. You average, that's because of the pi norm, pi inner product definition. But then this is pi inverse of V, PTV, and 1, which is just summation PTV, which is 1. Therefore, what we get is PT is pi plus I greater than equal to 2 summation alpha I pi fi, or pi inverse PT, which is what we care for this one, is all ones plus summation alpha I fi I greater than equal to 2.
So in the expression for alpha one, you used orthonormality of FIs under the
pi n product. Yeah. Now what is pi t plus 1? Pi t plus 1 is exactly W transpose pi t. Let's just, so it's W transpose pi plus summation alpha I W transpose pi fi. W transpose pi is pi itself. Pi is the right eigenvector with eigenvalue 1. And that's all. That's true here also. But these are with eigenvalues lambda 2 onwards. So this is alpha I, lambda I, pi fi. I greater than 2. All I want to claim is what we got for pi t. We got this summation for pi t inverse 1. For pi inverse pt plus 1, we have almost a very similar thing. We got 1 plus summation I greater than equal to 2 alpha I lambda I fi. So we can immediately make some conclusions. What we cared about was pi inverse pt minus 1's 2 norm. What is its 2 norm? The square of its 2 norm. It's going to be summation alpha I square, where I is greater than equal to 2. Similarly here, what do we have? Pi inverse pt plus 1 minus 1 2 pi square. What is this going to be?
Scale by lambda.
Scale. Each of them is scaled by lambda. In other words, pi inverse pt plus 1 minus 1 2 pi norm is equal to summation alpha I lambda I square I greater than equal to 2. We saw this. I want to relate it to summation alpha I square. So this is certainly less than or equal to lambda times I square. And this is since lambda is defined to be max of lambda 2 and mod lambda. So it's larger than every other thing in absolute value. Sorry, there's a square. Everything is square.
Even I think those alpha lambda.
That's square. Yeah. Everything is in squares. Yeah, everything is in squares. So this is lambda square okay. Everything had a square in it. So what did I put? I put a square.
That's the orthogonalities of the FS.
The orthogonalities of the FIs. Yeah. I'm using the full eigenvalue. Yeah. So what's happening here? So we were interested in this quantity. So we are asking how does this quantity change with time? And what are we noticing? That is every time step, that quantity, or rather the square of the quantity, shrinks by a factor lambda square. Now, if lambda is a number less than 1, this says very quickly it's going to go to 0. Once it goes to 0, It's going to go in 0 in the limit, but it's going to 0. That means it's getting closer and closer to this. So essentially, what we have proved so far is the total variation distance between PT and the stationary distribution is at most half times lambda to the power t of pi inverse the starting distribution 0, 1, 2. Each time the square shrinks by a factor lambda square, so the actual value is shrink by factor lambda, so we have this. And you know, this is a fixed quantity independent. This is a property of the stationary initial starting distribution. No matter that, as long as you escape these two obstacles, which is disconnectedness and bipartiteness, the random walk will converge to the stationary distribution. In fact, this quantity you can also say this is less than or equal to half of lambda t 1 over square root what is called pi min, and this is just that pi min is the minimum of pi v over t. This is at most. I'm just lower bounding that quantity. Yeah. What? This is t. This is t. This is a very important theorem for convergence of random walks. So, the random walk to converge, just look at this. The way to converge is look at its friend. This one, and you're splitting it very nicely. This is you're looking at the stationary distribution. The stationary distribution could have some very low probability response that could skew up things. Some vertices are extremely isolated, very rarely hitting, and that is going to skew up things. So that's possibly 1 over square root pi min. And the other one is how many steps you're going to take. These two will tell you, basically, these two are the only things to obstacle, and those two determine how much you have to, the rate of convergence of the total variation. So there's a lower bound also you can put similarly. We'll not discuss this, but I can point to your references in which you more or less have to take so many steps to converge. Okay. Questions? I'll take an extra 5-10 minutes. I want to finish the other thing because we are already in this understanding the writing things in the eigenspectrum in the basis, and the expander mixing lemma is just a simple consequence of this fact. So we'll just do that. But any questions so far? This should explain to you why once you have a reversible, irreducible random walk, it will converge to the stationary distribution. It's a very simple, clean proof of. This one, and then the proof of this is very quick, so we'll just finish this and wrap up for the day. Expander mixing lemma. So let W be a random walk reversible on the set of vertices V, and let G and H be two functions on the set of vertices. What is the expander mixing lemma going to consider? We are going to compare and contrast two quantities. We are going to look at the expected value of G of V. Let's write it as G of U, G of V And also another one which is expected. These look almost the same. If I'm going to make a slight change here, I'm going to pick U from the stationary distribution and V also independently from the stationary distribution. Like I pick two copies from the stationary distribution, U and V, completely independently. And here what I'm going to do is I'm going to pick U from the stationary distribution and V as a one-step random walk starting at U. So here is something I am picking like two vertices at random. Here is I'm picking an edge at random. And I'm asking what's the difference between, do these two expectations differ? Expectation of the same quantity but under different distributions. Okay, this is what we want to understand. And the expander mixing lemma says that if this lambda, the same lambda which we talked about is small, these two actually look identical to each other. And it's in terms of some other parameters. These other parameters we're going to define. So for any function f v to r, let's define mu of f is just the expected value of that function. F v pi. That's the expected value of the function. Notice if I had written the function in its eigenbasis. So I had written the function in its eigenbasis. What would this be? Where f is written in summation alpha I fi. It will be summation alpha I, expected value of fi. Expected value of, so fair enough. That's so it will be linearity. It's summation I alpha I, expected value of fi v in pi. Let's separate it. When f1 is the all ones thing, what's the expected value of the all ones? 1. The expected value of everything else. Everything else I think is orthogonal to the all ones. Therefore, they will all be, I want to claim expected value of all ones is 1. Expected value of fi, what is it? It is summation pi v fv. That's the expected value. That's the same as the inner product between f and the all ones in the pi norm, which is 0. So this is exactly alpha 1. That's all. So mu f, if I write a function f in its eigenbasis, alpha 1 is the expected value. And I also want to talk about what this is the mean. Let's also talk about the variance, which is sigma square f. What is the variance? It's the expected value. It's the expectation of the square minus the square of the expectation. These are, I need mu f and sigma f because I want to relate everything to mu f and mu. The expanded mixing lemma is stated in terms of means and variances. Let's write this also. Let's write down what these are. This I claim, this is exactly f, inner product of f in the pi norm. That's exactly that quantity. You agree? The second one is just alpha 1 square. What was this? What is f? Inner product with f and the pi norm. If f was equal to summation alpha I fi. This is just summation alpha I square minus alpha 1 square. So this is just summation alpha I square, I not equal to 1. Okay. All I want to claim is when you have the mean and the mean and the variance can be easily read off once you write things in the eigenspectrum. The mean is just what is the first one, the alpha 1, the coefficient corresponding to the eigenvector 1, and the variance is just the square of the remaining guys. And random mixing lemma states that if W have lambda, which is max of lambda 2 mod n and GH are two functions from B to R, then you're going to compare these two expectations. Expected value of G of U, H of V. When V is picked according to pi, U is picked according to pi, minus expected value of G of U, H of V. When U is picked according to pi, and V is a random walk. U. The difference of this is at most lambda sigma G sigma H. And equivalently, that is expected value of GU HV U from pi V from random walk of U minus this is mu G mu H. Writing G and H in the eigenbase. The main term was error term, that's all. Yeah. So, but we'll just see what random is. So I'm writing G in the eigenbasis. So it's summation alpha I, Fi, H in the eigenbasis, summation beta I, Fi. So the basis is F1 to Fn, F1 being all ones. So let's even make it this one. This is mu G, the all ones, plus I greater than 2, I greater than equal to 2, alpha I Fi. And this is mu H, all ones, plus summation beta I Fi, I greater than equal to 2. Okay. And let's look at expected value of GU HV, U coming from the random stationary, V coming from the random walk. I claim this is exactly summation over U by U. I'm going to take a step WUV, GU, HV. So there is a V also. This definition, if you just stare at it, this is just G, WH, into pi. This is what? So you can write G in the eigenbasis, WH in the eigenbasis, but WH when you apply it, so this is summation alpha I fi, then summation beta I w fi, fine. But w is an eigenvalue, therefore this is just going to become summation alpha I fi, summation lambda I beta I fi of pi. Orthonormality will say that this is just summation alpha I beta I lambda I going from 1 to n. All the square terms will vanish because of orthonormality. That's the nice thing of working with eigenbasis, with the orthonormal eigenbasis. This is furthermore what? Alpha 1 beta 1 plus I going greater than or equal to 2, alpha I beta I lambda I. Alpha 1 beta 1 was just mu g mu h, which we saw already. This is less than or equal to plus lambda into absolute value of I greater than or equal to 2, alpha I beta I. Cauchy-Schwarz. And this is just mu g mu h plus lambda sigma g sigma h. That's exactly what we wanted to prove. Okay. It's a simple consequence of the eigenbasis.
These lectures have we defined?
Huh?
Have we defined expander?
We have defined expander mixing. We'll define it. Expander. So expanders eventually are going to be something for which lambda is less than 1. That's all as an expander. This lambda isn't less than 1 is what is going to be an expander. In fact, less than a fixed constant. But the statement is this theorem is more, it's true for every lambda. We will use it for lambdas which are just bounded away from 1 also. This is true. Theorem doesn't use any of, it's called EML, but yeah. The very powerful theorem, lemma, we'll use it over and over again, various applications. Let's stop with this. I've gone well over time. Let's stop with this. The next lecture will be on Thursday. Thursday's lecture, I won't be here in person, but the class will happen here. I'm going to be at ICTS on Thursday. I will teach remotely. So it will be Zoom and stuff remotely. Class will happen here as usual. Yeah. Okay, stop this.